everyone, this is a fairly complicated section, 6.7. We're going to be talking about inverse relations and inverse functions. Once you get an idea what an inverse is, maybe it won't be so bad. We use that word inverse in math a lot, like the inverse of addition is subtraction, or the inverse of multiplication is division. So it's sort of like opposite type things, as we're doing something and then we're undoing it. Sometimes I like to think of we're going forwards and then backwards. First we add, then we subtract. So an inverse relation is a similar type of idea. For instance, if I have a function and the input of A maps onto B, then in its inverse, the input B would map onto A. It would go backwards. Basically, the X and Y's switch places in an inverse. So if we have this table of ordered pairs for this relation of X, Y's, what would be the inverse of these ordered pairs? For the inverse relation, we just switch the X and Y's. So this one was 0, 1. Its inverse is negative 1, 0. 2, 0 becomes 0, 2. 3, 2 becomes 2, 3. And 4, 3 becomes 3, 4. It's really that simple. Just switch the X and Y's. Now what I want to do is show you what these graphs look like. What does the inverse of a graph or a relation look like compared to the original? So here's the exact same tables that I did a minute ago. I'm put a graph in the middle. I'm going to plot these points of the relation. Then I'm going to plot the points of the inverse, and I want to see how they're related to one another. Here are the points of my original relation or function. Now I'm going to go ahead and graph the others. Here are the ordered pairs of its inverse. What happens with a relation and its inverse is it reflects across the line y equals x. Y equals x is this diagonal line that goes right here. And it makes perfect sense that it would reflect across that line because an inverse switches the x and y's. So after I drew that line, can you see how these points are a reflection of these right across the line y equals x? Okay, now I'm going to show you how to find the inverse of an equation. Here is an equation y equals x squared minus 1. I want to find the inverse to this equation. Here's what you do. Step number 1, switch the x and y. So if it's written in function notation, switch the f of x or g of x or whatever. Switch that function notation for y. And then switch the x and y. So this is going to become my x, this is going to become my y. So x equals y squared minus 1. And now solve this equation for y. And what you'll end up with is the inverse of this original. So we switched the x and y position. Now I'm going to solve for y. So first I will add 1 to both sides. So this is x plus 1 equals y squared. And now in order to solve for y, I need to undo the square. I'm going to take the square root of both sides. So y is equal to the square root of x plus 1. And I think we need the positive or negative square root of x plus 1. This equation is the inverse of that equation. Here's another function. This is a little simpler because it's just a linear function. What would be the inverse of this equation? So remember step 1, switch the x and y. So this becomes my x. X equals 2y plus 8. And now solve for y. So subtract 8x minus 8 equals 2y. Divide everything by 2, and I get x over 2 minus 4 equals y, or 1/2 x minus 4. So y is 1/2 x minus 4. And that is its inverse. Okay, first we had this function, y equals x squared minus 1, and we found its inverse, and it was right here. Now I want to go back and I want to look at the graphs of both of those and see how they are related to each other. So first I'm going to graph y equals x squared minus 1. So here's my original equation, y equals x squared minus 1. Now I'm going to graph y is plus or minus the square root of x plus 1. And there it is. Now what I did just to help you, because I didn't talk through it, I just graphed it. What I did to graph this is I chose numbers for x that would make this end up being a perfect square. So that's why first I made x negative 1 so that this would be 0 and y would be 0. And then I picked 0 because the square root of 1 is 1. So when x is 0, we have 1 and negative 1. And then I made x 3 so that this would be the square root of 4 plus or minus the square root of 4. And there's my 2 and negative 2. That's how I graphed this sideways. But sure enough, do you see how 1 is a reflection across y equals x? Do you see how it flipped right across that line? Another thing really interesting. This original relation, this original equation is a function. This one is not a function. Notice it does not pass the vertical line test. So inverses of functions are not automatically functions. It is possible for a function to have an inverse that is not a function, and here is a great example of that. I'll try to walk through the same exercise with the lines that we did. Here we took the linear function y equals 2x plus 8, and we found its inverse y equals 1/2 x minus 4. And I want to go ahead and graph those lines too, just to see what they would look like. Double check that they're a reflection across the line y equals x. Okay, here's a sloppy version of my first equation. Now I'll do the other one. And there is its inverse here. And you can see, even though it is sloppy on this whiteboard, it's best I could do, but you can see it still is a reflection of what over the line y equals x. These are both functions. When it's linear, then you know you're going to have functions with both the equation and its inverse. Okay, I haven't told you yet how to designate an inverse. So the inverse of a function f would be f, and you see this power -1. So this would be f inverse or inverse of f. That's what this means, and that's how you would designate that you want an inverse. So let's go through the steps to find an inverse function. Here is my function f of x equals the square root of x minus 2. And I want to start right off with what is the domain of this function. Because of this radical, this square root, you cannot have a negative square root, so therefore my x's are limited. So since I can't have a negative square root, my x's cannot be anything that would allow this to be a negative. So the smallest my x can be is 2, because 2 minus 2 is 0. So my domain, my x's, have to be greater than or equal to 2 in order for this radical, my radicand, to remain positive. Now I also want to find the range of this. Because the smallest this can be is 0, the square root of 0 would be 0, and then everything is going to be positive above that. So my range, my y's, are going to be greater than or equal to 0. I'm not going to have a negative answer in a square root. So here's my domain, here's my range. Okay, now I want to find the inverse of f. What is the inverse of f? So I'm going to go through the same steps I did before. I'm going to change this f of x to a y. Y equals the square root of x minus 2. And remember, my first step is to switch my x and y and then solve for y. So this becomes x equals the square root of y minus 2. Now solve for y. So my first step would be to get rid of this radical, undo the square root by squaring both sides. So x squared equals y minus 2. Add 2 to both sides, so x squared plus 2 equals y. So our f inverse is x squared plus 2. There's our inverse of f. Y equals x squared plus 2. There's our inverse. So now I want to find out what's the domain and range of my inverse of f. And remember that with inverses, the x's and the y's just switch. So guess what our domain is? Our domain is now x is greater than or equal to 0. And since our domain is x is greater than or equal to 0, guess what our range is? Our range is y is greater than or equal to 2. If x can only be 0 or above, right? Then my y's, it can only be 2 or above. And there we go. Notice the domain and ranges traded places. So my question to you is the inverse of f a function? And the answer is yes, because each input would have exactly one output. So yes, f inverse, or the inverse of f, is a function. Okay, now I want to explain something to you that can be confusing to students. So listen carefully. If you're zoning out, wake up on this video and listen carefully. When you're dealing with formulas that show variables that represent real entities, for instance, this is a formula for the distance a diver jumps off a cliff. The distance that they fall is 4.9 times the time in seconds squared. So this gives the distance in terms of the time. Let's say they want the inverse of this. The inverse function would be the time in terms of the distance. So you're asked to find the inverse of this formula. And so your first thought would be, well, switch the D's and the T's. And I'm going to say, don't switch them. Because D has to stand for distance, T has to stand for time. So you are still going to solve for T, but you're just not going to switch the letters. When you find the inverse of a real life formula, just rearrange the equation to solve for the other variable. That's all that you need to do in this case. So to find the inverse of this, you want to find the distance the time in terms of distance. By finding the inverse of this, just solve for the other variable. So how would we do that? Well, the first thing we would do is divide by 4.9. And then we would get rid of the squared by square rooting both sides. So our time is the distance divided by 4.9, or the square root of the distance divided by 4.9. And usually you would have a plus or minus with a square root, but since this is time, you're not going to have a negative time. We're only going to want the positive square root. So this would be your answer. This is how to find the time in terms of the distance. So let's say that the diver dove off a cliff that was 24 meters above the surface of the water. How long did it take for him to reach, or her, to reach the water? So you would substitute this D for 24, and you would find the square root of 24 divided by 4.9, and that would give you the time. I think it's about 2.2 seconds or something like that, but that's how you would do it. Okay, here's another formula that represents the distance in meters that an object has fallen, determined by the velocity in meters per second. So what I want you to do is find the inverse of this formula. This is your lesson check. Were you listening carefully about my instructions in finding the inverse of formulas? Bring that in to me, showing that you did, and don't stop this video because we have a lot to cover still. But your lesson check is the inverse of this formula. Okay, there are some functions that are one-to-one functions. You already know a function takes each input matches to exactly one output. By definition, that's a function. A one-to-one function means that each output maps to just one input. So you can go forwards and backwards. If each output has only one input in a function, then it's a one-to-one, which means not only is the function the main equation of function, but its inverse will also be a function. Those are called one-to-one functions. If a function takes A and maps it onto B, then its inverse should take that B, right, and map it back to A. That's the whole point of an inverse, is going back and forth. So if this goes here, the inverse should go back. This is one way that you can tell if equations are inverses or not, especially one-to-one inverses. And that's what we talked about last time, these composition of functions. If you put one inside the other, so if I take f inverse of f of x, in other words, I put f into its inverse, I should get out just x. If I have f of f inverse of x, which means I put the inverse of f into f, all that should come out is x. Whatever I put in comes back out. Right? That's the way this should work, because one undoes the other. So whatever I put in and then it reverses, that's exactly what I should get back out when I put them in both. Okay, so we're going to walk through this. I have this function. It's 1 over x minus 1. First thing I'm going to do is I'm going to find the inverse of this. And then I'm going to do a composition of functions. I'm going to put one inside of the other, one at a time, and see what comes out. All right, see how this works. So first I'm going to find the inverse of this by switching my x and y. So x equals 1 over y minus 1. And now, notice I switched them. Now I'm going to solve for x. So first I'll multiply both sides by y minus 1. And now I'm going to divide by x. Y minus 1 equals 1 over x. And now I'm going to add 1. And my inverse is y equals 1 over x plus 1. There's my inverse. So here's my original function. Here's its inverse. Now I'm going to do a composition of functions. F of f inverse of 1. So remember, I go from the inside out. So first I'm going to put 1 into my inverse. So that would give me 1 over 1 plus 1. That would equal 2. So that's 2. Now I'm going to put 2 into here, and I get 1 over 2 minus 1, which is 1 over 1. And what comes out was 1. Okay, now I'm going to do the same thing, only backwards. So I'm going to find f inverse of f of 1. So now I'm going to first put 1 into f, and then that into its inverse. And I'm in trouble, because if I put 1 here, 1 minus 1 is 0. So this particular number does not exist. So if they ask for something like this, it does not exist, because this is outside the domain of this function. This domain is x can be anything but 1. And so that's what you would write. This does not exist. But just for curiosity's sake, I want to see if I put a different number. If we'll get the same thing we put in. We should. This isn't in the book, but I just want to do this for fun. Let's try 2. Let's make this 2. So let's put 2 in here. So 1 over 2 minus 1 is 1 over 1. And so we get 1. So now I'm going to put that into my inverse. I'm going to put 1 into my inverse. 1 over 1 plus 1, which is 1 plus 1. It equals 2. Do you see? That's what inverse functions will do to each other. We put a 2 in, we got a 2 out, and that should work. The only reason this other one didn't is because 1 was not in the domain undefined. There's a got it example in your book for g of x to go through the same exercise, and they do the same thing. They have you put into this composition of functions something that doesn't exist in the domain. It's outside of the domain, so you have to write, it's outside of the domain, so it does not exist. I want to do this, but I want to tweak it a little bit to show you something pretty cool. So first, here's g of x. I want to find, the first step is to find its inverse. So let's do that. So I've switched my x and y, and now I want to solve for y. So x times y plus 2 equals 4. which means y plus 2 equals 4 over x, which means my G inverse is equal to 4 over x minus 2. Now I have my G and its inverse. All right, what I want to do is just put the inverse into G. Just put this into G and see if I get x out, right? I'm not going to put a number. I'm just going to put this into this and see if I get x out. Does one undo the other? Which means I'm putting this 4 over x minus 2 in place of x, and this looks really gnarly. So I may edit this out, but we'll see. Okay, so notice I put my inverse, which is 4 over x minus 2. I put all of that in place of my x in G. Do you see that? The inverse into G. So I put 4 over x minus 2 where the x was. And now I'm going to simplify this. And negative 2 plus 2, those cancel out. And I just end up with 4 over x, 4 divided by, so this means 4 over 1, divided by 4 over x. Remember, when you divide, this becomes multiply, x over 4. These cancel out. What do you know? I'm left with x. That's super cool. If it is a true one-to-one function, then the reverse should also work. Now I'm going to take g of x and put it in my G inverse. I'm going to try the reverse because it should work both ways. I'm going to put this into here. Okay, we have a complex fraction, which makes this tricky. But remember, this means 4 divided by 4 over x plus 2. So let's just go back to elementary. 4 over 1 divided by 4 over x plus 2. So if I'm dividing by a fraction, I multiply by its reciprocal. So this means times x plus 2 over 4. Notice my 4's cancel out, and this whole thing simplifies to be x plus 2. So now we have x plus 2 minus 2, which is x. And it worked both ways. This is what inverse functions do. So that was a really lot to cover for one section. I tried to do it methodically and step by step. Hopefully it made sense what inverses do, how you can just find an inverse of an entire function. And that's pretty cool. Have fun with this. Be sure to ask all the questions that you want, and I will see you guys next time.